Hello friends, in this session we will be discussing about cylindrical rotor. Let's begin. Now see here, we know that in order to make induced EMF sinusoidal, we need to make flux sinusoidal. Why? Because already we have discussed that E conductor is proportional to B, right? So in order to make E conductor sinusoidal, I need to make this particular flux density sinusoidal. So now let us focus on this B. In order to focus on B, we have got two types of rotor. Number one is cylindrical type of rotor. Number two is salient type of rotor. Anyways, let us think of cylindrical. See here. Cylindrical rotor. Right now, we are in step 1. Step 1 means, sir, step 1 means we need to make flux density sinusoidal. Means we are actually trying to make it sinusoidal. It will not become exactly sinusoidal, but we are trying our level best to make it sinusoidal. Anyways, let us talk about cylindrical rotor. See here. If we think of, this is a rotor, for example. This is a rotor. Right? Now, let me have two conductors here. One conductor, another conductor. Okay. Now, what I am saying is, for example, here I am giving dot currents and here I am giving cross currents. Then, how is the flux? The flux is going to be this way. Right? So, this becomes north pole and this becomes south pole. Because see here, where we think of flux, flux is moving this way, which means, see here, flux will be outgoing from this rotor piece, which means this becomes north pole. And here if you think of, this is, if this becomes north pole, this has to be south pole. Already we know that. Anyways, let us think of stator now. This blue is stator, bullseye, right? And let me have a conductor here. Now see here. Am I interested in the flux? No. I am interested in the induced EMF of this particular, what do you say, conductor, armature conductor. So now see here. I want this induced EMF here in this particular conductor, whatever induced EMF it is. Means, see here. For example, I am rotating this rotor in this direction, let us say. This is a cylindrical structure of the rotor. I am rotating it in, for example, this particular direction. Now you please tell me how will be the induced EMF here. Induced EMF here means, see here. This is the field. Field is in upward direction, right? North. Outgoing from the north, right? This is the field. Now, what I was saying, this particular field is moving in this direction, which means with respect to the field, conductor is moving in opposite direction, which means, see here, virtually this conductor will move in this direction or not. With respect to field, this conductor virtually moves in this direction, which means, see here, this is going to be the flux, this is going to be motion of the conductor, this is going to be induced EMF. So here I am going to get dot induced EMF, right? Let me have it in blue, dot induced EMF. Now, I am interested in whether it is going to be sinusoidal or not, because see here, let me think of one more conductor here. See, don't you think that here also if you say, here also there has to be some or the other induced EMF? Of course, here also there will be some induced EMF, here also there will be some induced EMF, but what is going to be the value? Value in the sense, how will be the waveform of my induced EMF with respect to time? So this has to be, we know that it has to be sinusoidal, but in order to make it sinusoidal. What has to be done? My flux density which is there, it has to be sinusoidal. Now, when my flux density has to be sinusoidal, so first of all, let us see how the flux density will be there for this particular structure. Let us say, for that, I take a scissor, and I'll cut it here like this. Cut it here like this. Cut from here. The moment this is cut, what is going to happen? See here. I am going to make a cut over here. Cut this from here and then just open it like this. Cut this from here, open it like this. The moment I open it, I'll make it like this in a straight way. So now you please tell me here, this conductor which is there, it has to be placed in slots, right? No, this conductor which are there, those conductors will be actually there in the slots, rotor slots, right? So let me have those conductors here. See, this was the rotor structure, linear. Let me have the slots. Let me have two slots here. Is it right? Now, see here. Now, here we have this conductor which is having dot. Here we are having this conductor. This is whatever is happening here is in space, right? Here we have dot conductor and here we have cross conductor, right? Now see here. I am expected to find the MMF waveform in space. Let us try to think how will be the MMF waveform in space for this one. Let us see. Before that, let us think of what is MMF. If you remember Ampere's law. Ampere's law was that I enclosed, current enclosed is going to be closed integration of h bar dot dl bar. What does this mean, sir? See, it is very simple. Let us just ignore everything. Let us just ignore this concept. Let me think of transformer. See here. Let us think of transformer. In case of transformer, if you remember here, this was a transformer, for example, right? And let me have windings here. N number of turns let us have, right? Now, let me provide it some supply. Let me supply it with some sinusoidal voltage, right? So here, current flows, I naught current flows, right? Now, basis of transformers only. Because of this current, what is going to happen? This current is going to move in this way, this way, this way. Because of this, what is going to happen? Flux is going to come. Flux is going to come or not? Right? Now, see here. What is the meaning of current enclosed? Current enclosed means what, sir? See here. Don't you think that this is a closed path of a flux? Closed path of flux? Yes, it is. Closed path of flux. Right? So, for this particular closed path, how much is the current enclosed? Let us see. For this closed path, how much is the current enclosed? Let us see. So, here if you think of, this is I naught current is there, right? So, for this closed path, if you think of, this is the closed path. So, how much is the current enclosed? Focus here, focus here. 1 ton, second ton, third ton, n number of tons. Which means, if it was just imagine, if here rather than having n tons, if I have only one single ton, then in that case, how much is the enclosed current? I naught. If it was only one single ton, see. Let me consider one more. See here. These are basics and they are very important. See here. These are basics and they are very important. Yeah. Let me just consider here 1 turn. Right? Let me have some, sinusoidal voltage applied here, let us say. And then you have this I naught. Alright? Now, let me have this. So, I naught is flowing, which means there has to be flux here. So, for this closed path of the flux, if you see, how much is the current enclosed? How much is the current enclosed here? It is nothing but I naught only. Why? Because see here, what is going to happen when I move like this, in this way, this way, how much is the current enclosed? Only one, I naught. For this closed path, I naught is the enclosed current in the closed path. Similarly, here, I naught plus I naught plus I naught plus I naught. How many turns are there? N turns are there. So, N times I naught. So, here, if you think of what is MMF, N times I naught. So, N times I naught is nothing but MMF only, no? Number of turns into current. Right? So, MMF is what? MMF is nothing but enclosed current in the closed path. That is the MMF we have understood from the example of transformer. Let us apply the same there. See here. Yes. Let me show the MMF in space by green. This is MMF, let us say. MMF. Now, if you see here, what is going to happen? Is it dot? Forget about it. You please tell me, for this particular closed path, how much is the enclosed current? I. For this closed path, how much is the enclosed current? I. For this closed path, how much is the enclosed current? I. For this closed path, how much is the enclosed current? This closed path means this total. See here, again. Focus here. See. For this closed path, how much is the enclosed current? I. For this closed path, how much is the enclosed current? I. Right? Now, see here. This current here. See this. This particular current here which is there, it is going to be what? IF current only, no? IF current it is. Current I only. So, here if you see, what is going to happen? For this closed path, how much is the enclosed current? I. For this closed path, how much is the enclosed current? This closed path. How much is the enclosed current? I. For this closed path, how much is the enclosed current? I. Now, for this complete closed path, how much is the enclosed current now? For this closed path. See, both have opposite polarity. This is dot, this is cross. Equal current only has to flow. Which means, here if you think of this is dot and this is cross, which means enclosed current here is going to be 0. Why? Because they are equal and opposite. This is a coil, right? For example, this coil is X and X dash. So this is X. This is X dash. Back to back. Right? X dash. Back to back. Connection is there. So what is going to happen here? Just see. This is for example entering current, right? This is X and this is X dash. X dash is entering current here. Going there. Which means current enclosed here is going to be what? This current plus this current, and direction which is there is in opposite direction. Opposite, no? So that is the reason enclosed current here will be 0. So now we know that MMF is what? MMF is what? Nothing but current enclosed. So here for this one, if you see, how much is the enclosed current? I. So here it was 0. Here it goes I. From here to here, if you see, same I current is going to be there. From here to here, if you think of, same I current will be there. From here to here, if you think of, it is going to be 0. So this is going to be the MMF wave. I hope you are understanding it. Now, you please tell me, is it sinusoidal? No. This is 100% non-sinusoidal. Right? Now see here. Actually what happens is, forget about this. See. You please tell me one thing here. What is the pole going to be here? See, very simple. Do you believe that it is a rotor structure? Yes, it is a rotor structure. This is cross, this is dot. This is cross, this is dot, which means this is entering current, outgoing current. So this complete portion is going to be north pole of the field, and the MMF due to this north pole of the field is going to be in this particular fashion. Am I right or wrong? 100% I am right. So this is going to be non-sinusoidal. Now let us see. Now you please tell me one thing. Here if you see, for one pole, see here, focus. Here you have two poles, north pole and south pole, and for two poles you have two conductors, or we can say for two poles you have two slots. Chill. See, let me tell you one more thing here. Just focus. See, what I'm saying is, in a practical rotor, if you see, do you have only one conductor? In a practical rotor, do you have only one conductor here? Answer is no. Let us see what happens in a practical rotor. See, what happens is, let me just show it here. Yes. See, in a practical rotor, if you see, no, this is going to be, let us say, this is the rotor, linear way. So here I will have slots. This is going to be, let us say, those two slots. Same two slots I am having. Now here if you think of, here you have many conductors. Let us say in this case you have four conductors. In a practical one, you have many conductors. You don't have one single conductor in a practical rotor. So here if you think of, but then yes, direction will be dot, dot, cross, 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 and cross. Right? So now all are cross, all are dot. What is going to happen? What is going to happen here? All are cross, all are dot. Entering, outgoing, which means flux is in, outgoing from the rotor, which means this becomes north pole of the field. 100% it becomes north pole of the field. We are trying to see that what will be the difference. See here, we have considered one conductor per slot for understanding purpose, but it is my duty to tell you that in a practical rotor, we don't have one single conductor, we have many conductors. Anyways, let us see it. Let us think of MMF wave here in space, which is there. Let us show it by green. MMF, right? Now, see here. See here, focus, very easy. If you think of from here to here, for this area, how much is the I enclosed? How much is the I enclosed? Let us say it is I plus I to I. Right? Now, from here to here, how much it is enclosed? 4i. 1, 2, 3, 4. No? From here to here, if you think of, how much it is? 4i. From here to here, if you think of, how much it is going to be? 4i. From here to here, if you think of, this is going to be, from here to here, if you think of, from here to here, how much is the current enclosed? 1, 2, 3, 4, 5, 6, 6i. And from here to here, if you think of, it is going to be what? 8i. Right now, from here to here, if you think of this particular closed path, if you think of this closed path here, then you understand that 1, 2, 3, 4. So, is it 6i and 8i? Here I have done a purposeful mistake. What is that mistake? See here. When I am saying that from here to here, if you think of, is it so? No, because see here. These are 2 with dot. These are 4. For example, if you are considering this closed path. If you are considering this closed path, let us say this closed path, if you consider, then for this particular closed path, if you think of, what do you have? See here, you have 4 dots and you have 2 crosses, which means you have 2 dots left. 2y only, no? Whereas if you think of this complete one, this complete area, it is going to be 0, because 4 dot 4 cross get cancelled each other. So how is the wave going to be there? 2, 4, 4, see here, from 2 to 4 increasing, and then again 4 to 2 increasing, and then we have 0. Let me draw it with green. So here if you think of, this is 2, so this is 2, and here if you think of, this is going to be 4, and then this is constant, and then this is again 4, 2, 0. I hope it is clear, right? See, from here to here, if you see, for this complete one, it is going to be 4 only. For here it was 2, for here it was 2. So what do you observe here? What do you observe here? Here in this case, you have slope. You have this slope. And here if you think of jump, directly it is, alright? Here in this case, you will have slope. Anyways, what I am saying, see here, let me consider, see, yes, what I am saying is, let me consider this one. Let me think of, now we have taken only 2 slots, right? And we have taken 2 slots for 2 poles. See now, here 1 pole, 2 poles. We have 2 slots, which means we have taken how much? 1 slot per pole. Now, let us take 3 slots per pole and then see what is going to happen. See here. The moment I have 3 slots per pole, which means this is rotor, right? Let me write 3 slots per pole. Okay. Now, this is going to be the rotor. In this, I will have 3 slots. 3 slots per pole. So this is 3, 6, right? So this is going to be right. This is going to be it. Now, see here. Let us see what is going to happen. Let me just take it this way. Let me just erase this. Right? Now see here. Very easy. 3 slots per pole. See here now. We know that in 1 slot we will have so many conductors, right? In the previous one, if you see here, in a practical rotor we have not 4, we can have n number of conductors there, right? So here if you think of, but for simplicity here, for understanding purpose, let me only consider 1. Let me consider only 1, because at the end if you see here, all are dots only, right? For this particular slot, 1 slot if you think of, all are going to be dots only, all are going to be cross only. So this equivalently we can consider it to be 1 conductor only, no? For simplicity I am considering. Anyways, see here. Now I'll have, let us say, conductors here. These are crosses and these are going to be dots, right? Now see here. Now let me think of MMF wave here. Green as usual. Actually, student may ask me, sir, but we want flux density, you want flux. Why are you considering MMF only? See, there is a reason. There is a small difference between MMF and flux density. What is that difference? We will come to know. See here, actually what happens is, for some time, up to some time, flux and MMF are proportional to each other. Up to some time, flux and MMF are proportional to each other. When they are not proportional, we will discuss when time comes. For that is the reason right now let me only consider MMF. That is the reason. Anyway, see here. Now, if you think of here, for this area, how much is the current enclosed here? I, right? For this one, for this closed path. How much is the current enclosed in this closed path? 2 times I. So this, for this one it was I, for this one it is 2 times I. Again, from here, see here, I am not considering only this part, I am considering this total. For this closed path, if you think of, how much is the flux? How much is the current enclosed? 3I. Am I right or wrong? Then, see here, from here to here if you think of, it is again going to be 3I only. Again, from if you think of here to here, it is again going to be 3I only, because 1 to 3 dot currents. Now, when you go from here to, let us say here, for this closed path, this one, for this closed path, what is going to be the enclosed current for this closed path? What is it going to be? This is, see here, 3 dots, 1 cross, which means this is going to be 2I. Means 3 are in, let us say 3 are in one direction, 1 is in another direction, and we know that all are going to be equal. So these 2 are 1, only 2 left, no? Similarly, if you see here, for this closed path, let us say, for this closed path, how much it is? It is going to be 3 dots plus 2 cross. In this case, 3 dots plus 2 cross, which means 2 are in opposite. They will cancel. So here I will have only I. Right? And if I think of here, 3 dots and 3 crosses. 3 dots and 3 cross for this whole. So here I will have 0 MMF. Right? So let us draw the MMF waveform. From here to here, it is absolutely going to be 0, because if you have closed path here, right? So 0 current enclosed here, 100%. Now see here, this is going to be 0 MMF. From here to here, if you think of, this is I, right? This is I, like this. Then if you think of here it is 2I. From here to here, if you think of, this is going to be 2I. Then from here to here, if you think of, this is going to be 3I, right? And then this 3I goes up to here, and then again it is going to be 2I, then again it is going to be 1I, and then it is going to be 0, right? Now, so here if you see, here the MMF waveform that we are getting is a stepped MMF. This is stepped MMF, right? It is a stepped MMF. Now you please tell me this one. When we had only one slot per pole, see here, I am repeating, here we had what? We had one slot per pole. One slot per pole was there here. So in that case, we got this one, right? But now when slots per poles are increased, I am having step wave, right? So is it better sinusoid than previous? Better sinusoid than previous? Right now, this is quite better sinusoid, right? Previously, it was this way, 1 and it's gone. But now here it is some way sinusoidal, some way. So now if I go on increasing, so now what do you understand from this? Moral of the story. Let us find out conclusion number 1. Conclusions. What is the conclusion? Conclusion number 1 is what? Yes, tell me. Slots per pole have to be increased. So if you see here, slots per pole have to be increased in order to get more sinusoid. I am not saying exact sinusoid, but I am saying more sinusoid. I hope you have understood this. Anyways, let us think of one more. For example, see here. I have, let us say, those 3 slots as usual. Let me have 3 slots per pole. Now see here. What I am saying is, because if you see here in the previous case, if you see this one, where it was, we talked about, right? We said that in one slot there will be n number of conductors, right? Any conductors, right? Now let us see what should be the number of conductors. Let us see what should be the number of conductors. So see here. Right? Yes. So now if you see here, what I am saying is, see, I'll have some conductors here, right? Conductors will be there. Let me consider one conductor only at first. Dot, dot, dot. And let me have cross and cross conductors. So now if you see here, if I am thinking of MMF, see, what I am saying is, no, rather than thinking of stepped wave first, let me impose sinusoidal wave. Means what, sir? Let me just impose sinusoidal wave here. This is sinusoidal wave. Let me just impose it, no problem. And then we will see what can be done. See here. What I am saying is, let me consider, see, you will understand everything. You will say, sir, how did you take it, sinusoid and all? You will understand. Just wait. Give me 2 seconds. Let me consider this slot angle as 10 degrees, 10 degrees and 10 degrees. Slot angle says 10 degrees. Slot angle means angle, spatial angle between the slots. So now, for example, this distance between these 2 slots, 10 degrees, 10 degrees, 10 degrees, let us consider. Now see, let me just think of sine 10. What is sine 10? Sine 10 degrees, if you think of, let me calculate. See here. Yes. If you think of sine 10 is 0.1736. Right? Let me think of sine 20. Yes. Sine 20, if you think of, it is going to be 0.3420. And if you think of sine 30, we already know that it is going to be 0.5. Right? Now, relax. See here. Let me consider the difference between these two. Let us think of difference. What is the difference? See here. Difference means 0.3420 minus 0.1736. So this is going to be 0.161, 0.1684. Right? And let me consider the difference between this. You will understand everything, don't worry. What is the difference? 0.5 minus 0.3420. To be 0.158. Yes. Now see here. What I am saying is, let me have 17 conductors here in the first slot. Let me have 16 conductors in the second slot, and let me have 15 conductors in the third slot. Means now conductors will be increased. Right? Now see here. What did I observe? My observation was that if I have 17 conductors here, then if I have 16 conductors here and if I have 15 conductors here, what is going to happen? Let us see. See here, when I think of this particular, this one, let me think of this particular closed path. Let me think of this closed path. When I think of this closed path, I will have 17 conductors. So let me have MMF here like this at 17. Right? So this is going to be 17 up to here also it is going to be 17. Let me consider this one, this closed path. If I consider the second closed path, this closed path, what do I have? I have 16 plus 17. 16 plus 17 means it is again more increase here like this. 16 plus 17 is going to be 33. 16 plus 17. So this is going to be 17. This is going to be 33. From here to here. Total is going to be 33. And if you think of this closed path here, or this closed path, this complete, these three slots, this closed path, if you think of, how much you get? You get 17 plus 16 plus 15, which is equal to what? 17 plus 16 is 33. So 7 plus 16 is 33. What is 15? 15 is going to be 33, 43, 48. Right? So here there is going to be 48. Right? So now you think of here. This is going to be 48 only. Then again this is going to be this way somewhere. And then here. I hope you are understanding it. So now you please tell me, is it better than the previous? Better than the previous. Previous also you got stepped MMF only. But now, here if you see, what has happened here? Here if you see, what has happened here? You firstly impose the sine wave. And then by using sine function, you actually found out how much conductors should be there per slot. Conductors per slot. You identified it. And then you have this stepped waveform again. But this is quite better than previous. Better than previous or not? Yes, 100%. So, what do you conclude from here? What do you conclude from here? Let us see. See here, do you agree with me that since this is cross, this is dot, this has to be north pole or not? North pole of the field. This is cross, this is dot. Flux will be out of the rotor. This is going to be north pole. We already know. Now, see here. See here. We know that at the center of the pole, flux is going to be maximum. At the center of the pole, flux is always going to be maximum. Whereas if you think of here if you see here in this area, if you see, this is going to be what? Here flux is 0, or you can say 0 mmf here. mmf is equal to 0 here. And this axis, if you think of this axis, already we have discussed in the previous session that it is called as interpolar axis. Or we call it as Q axis. And this axis in which mmf is maximum is called as D axis. Let us think of this one in terms of a rotor. See here. Let me have rotor here. Let me have rotor. See here. Let me have rotor here like this. Right? When I say that this is north pole and this has become south pole. There have been some conductors here, right? 3 slots, right? And then what is north and south? Now we know that if you think of here, this is going to be the interpolar axis. Means in this particular axis, if you see, mmf is going to be 0. Why it is 0? We have already discussed. Then here if you think of this axis, this here, field is going to be maximum. This is the reason this one is called as D axis, or also called as direct axis, whereas this is interpolar axis, also called as Q axis. Anyways, moral of the story is, see, so from here what do we infer? We infer that from interpolar region, or we can say from interpolar axis to center of the pole. Is it center of the pole? Of course it is center of the pole, right? Center of pole. See here, from interpolar axis to the center of pole, conductors per slot is reduced depending on the sine function. Again, from interpolar axis to the center of the pole, conductors per slot is reduced depending on sine function. See, now here you had 17 conductors, here you have 16, here you have 15. So let me just add it. Second one. So from interpolar axis to the center of the pole, the number of conductors per slot is reduced depending on the calculation of sine function, because we have seen here already how it is going to happen. Here, no, here. Anyways, now if you think of, is this particular wave, is it sinusoid? No. We have tried our level best to make it sinusoid, but it is not at all becoming sinusoid. What waveform we have here is nothing but a stepped waveform only at the end. We are all getting stepped waveform. So, means that, see here, if you have stepped waveform here, which means the induced voltage in the conductors, means, for example, see here, See here. See here. If you think of this one, if you just see this particular, what do you say here? Here in the air gap, if you see the flux distribution is stepped this way, is stepped, right? This is MMF. MMF distribution is in stepped way. So what is going to happen? The induced EMF in this conductor, will also be stepped only, which means there will be harmonics in the induced EMF as well. Harmonics in induced EMF as well. So now the moment we have harmonics in induced EMF also, what is going to happen? If harmonics are there, they have to be made zero. Why? Because if harmonics are present in the induced EMF, which means whatever load you will have connected, currents will also have harmonics, which means currents will also be non-sinusoidal, which means RMF is elliptical, which means torque is not constant. So what will happen? Wear and tear. Just imagine how this induced voltage thing, this particular sign thing is been. We are thinking of it in a detailed manner. Anyways, this is what it is. So in this step 2, what we will do is, we will try to make this stepped EMF as sinusoidal. We'll see that in the next sessions. Anyways, let us think of mechanical engineering point of view. Now, let us think of mechanical engineering point of view. So now, let us think from mechanical point of view, means mechanical engineering point of view. Sir, we are all electrical engineers, still mechanical engineering point of view. You will understand, wait. See here, what I am saying is, let us think of speed of rotation. I mean to say, which rotor, salient pole rotor or cylindrical rotor, which one has to be rotated at higher speeds or which one has to be rotated at lower speeds. So in order to think of cylindrical, whether it is at higher speeds or lower speeds, we will have to firstly compare it with salient. So let us think of salient here. Let us think of salient poles. Firstly, if you think of, in case of salient, if you see, what is going to happen? You are going to have a rotor like this. Right? And on top of this, you are going to have stator. Now, you please tell me here. See, focus. Very easy. See here. Do you believe that here in the air gap there will be some air? Air will be there in the air gap, of course. So let me call this as natural air. Natural air is there in the air gap. This is all air gap, right? So air will be there in the air gap. What else can be there? Now, see here. If I want to rotate this one in this direction, let me take red. If I want to rotate this one in this direction, let us say, clockwise direction, means this is the rotor, salient rotor. If I want to rotate this rotor in this direction as shown, this direction as shown. So if I want to rotate this one in this direction, which means what should happen? Whatever natural air was here, that has to get transferred here. Means, see here, this is the salient rotor. This rotor has to be rotated, Let us say this rotor has to be rotated in this direction. The moment this rotor has to be rotated in this direction, which means whatever natural air you have here, has to be flown here. Means natural airflow should be in this direction. Again, see here, this is the salient rotor. Salient rotor has to rotate in this direction, which means whatever natural air you have here, if this rotor is rotating in this direction, this air has to flow in this direction. So, natural airflow. So, natural flow has to be in this direction, airflow. Now, because of that, what is going to happen because of that? Because of that, noise will be increased. Noise will be tremendously increased. Then, next thing what can happen? Friction and windage losses will increase. Friction and windage losses will increase. How? Because see here. See again. You have this one, salient pole. Now you have air here, right? So now what is going to happen? Some energy of my salient rotor will be absorbed by this air as well, no? See here again, you are not understanding the point. Again. This air which is there in the free space, in this air gap, see here, this is going to be salient pole, this is going to be the air, right? So now, because of this air, this particular salient pole will face some friction or not? Yes, means this particular salient pole will face some friction due to air. That is the reason there will be friction and windage losses. What are friction and windage losses? Time will come, we will discuss them in detail, don't worry. But right now, for time being, just understand one thing. This is the salient pole. This is going to be air here. If I want to rotate this one here, which means this whole air has to travel here, right? So noise will be more and friction and windage losses will be more, which means that salient pole cannot be operated at higher speeds, which means salient rotor is operated at lower speeds only. Salient pole is operated at lower speeds only. Now, let us think of cylindrical. When we think of cylindrical, let us say, cylindrical rotor is like this, right? Let me have shaft key. And above this I have stator. Now, if you see, air gap is same everywhere. Air gap is going to be same. The moment everywhere air gap is going to be the same, air is going to be same here everywhere. Same or not? Air is going to be same. Which means, now see here, if my cylindrical rotor has to rotate, for example, this is a cylindrical rotor. Let me take one more. For example, this is going to be my cylindrical rotor. If this one has to rotate, it can happily rotate. Why? It will rotate smoothly because there is sufficient, air gap for this particular air to travel here. Meaning that, see here, mechanical forces. Yes. So if you see here, what is going to happen? What is going to happen here? This force means this air which is there, this will not have any mechanical forces on this particular rotor. Meaning that, see here, this is going to be a cylindrical rotor. Cylindrical rotor wants to rotate in this direction, let us say. The moment cylindrical rotor wants to rotate in this direction, this air will flow smoothly around it. Air will flow smoothly around it, which means noise is going to be less. Which means friction and windage losses is going to be less. Which means it can rotate at higher speeds. So, see here, cylindrical rotor can rotate at higher speeds, whereas salient pole which is there, it is going to rotate at lower speeds. This is what is the conclusion. Let me just add it in the conclusion section. Yes. Let me think of third one. Cylindrical rotor can rotate at. See here. First one, if you think of first one was what? Slots per pole have to be increased. So the moment slots per pole have to be increased, which means number of poles that can be incorporated in the same area will be reduced or not. See here. This is going to be the rotor, right? Now, what I am saying, we are increasing the slots per pole. Let me have 333 for example. Let us consider that this one is for N pole, this is for S pole, this is for N pole, and this is for S pole, let us say. So now, see here, what we are trying to say is, at one time we say that slots per pole has to be increased, right? But now if you think of actually what is going to happen, see. So actually if you see here, when we are increasing slots per pole, for the same structure, if you see, if my slots per pole are increasing, because see, slots can be, see, either you can have 50 slots or 100 slots or stuff like that. But if you think of, when I am saying that slots per pole has to be increased, which means number of poles that can be incorporated in the same area will be reduced. For example, if I had no condition on this, means slots per pole increase and all is not there, for example, then you can have 10 poles also, 12 poles also. I may consider no, rather than 3, what I will do is I will consider these 2 only, 2 slots per pole. Then in that case I will get 1, 2, 3, 4, 5, 6. Then I will say no, let us consider 1 only. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 slots you have got. 12 poles you have got. It can be done or not. But since we are saying that no, in order to have more sinusoidal flux density, we are going to have slots per pole increased. Slots per pole has to be increased. So, because of this necessary condition, this is the necessary condition, right? This is the necessary condition. Because of this condition, the number of poles that can be incorporated here is going to be less. So, let me conclude. Fourth one, what is that? Since slots per pole is increased, number of poles Since slots per pole is increased, number of poles that can be incorporated in the same cylindrical diameter is reduced. This is going to be the disadvantage. I hope you are understanding the point slowly. Now, let us think of another one. Now, let us think about diameter of the cylindrical rotor. See, when we talk about diameter, let us see. What is the meaning of diameter? See here, very simple. Let us take two rotors. I will have one rotor here, let us say. And I will have another rotor. Yeah. Both are rotors only. This is rotor 1, this is rotor 2. Now, we know that on this rotor there will be some slot, some insulation, and over that I will have a conductor, right? Similarly, if you see here also I will have some slot, I will have a conductor, and here insulation is going to be there. Insulation has to be there, right? Why? Because conductor is electrical conductor, and this particular, what do you say, rotor is nothing but iron, right? Iron is what? Iron is a magnetic material, but at the same time it is going to be what? It is going to be electrical conductor as well. So it should not get short circuited. That is the reason. Because see, this is iron, right? This is also electrical conductor. This is electrical conductor. This one, this is conductor, and this slot, or you can say this complete rotor, it is also what? Electrical conductor. So since there should not be any short circuit, what we prefer? We prefer that insulation has to be there in between. So here insulation is going to be there. Insulation is going to be there in between. This is insulation, green. Insulation. Now see here. Let me rotate this in this direction, for example, and let me rotate it with, let us say, 100 RPM. Okay, and let me rotate this one also at 100 RPM. Means these are two rotors of different diameters, and what I am going to do is I am going to rotate them with the same speed. So this is 100 RPM, this is also 100 RPM, rotating in 100 RPM. Now what is going to happen? See here. Let me introduce you to a term called as radial velocity. Radial velocity. Chill, no problem. Velocity means what? Speed, right? Speed means distance upon time. Distance upon time or not? Right? Now, if you think of here, what I am saying, see, distance upon time. Now, radial velocity distance means what? See here. See, you please tell me one thing. If in 1 minute, this rotor, red one, if it is rotating by 100 rotations, then this one also, blue also same. Blue also in 1 minute will rotate 100 RPM. Right or wrong? So 100 RPM speed is same, which means can I say that the time taken will also be same? Time taken for this one to rotate at 100 RPM to make 100 revolutions. See here, very simple. Time taken by this rotor to rotate 100 revolutions, and time taken by this one to rotate 100 revolutions will be same, right? So which means that time is going to be constant, no problem. Time is not at all the concern. But let us think about distance. See here, see, if you think of this particular rotor, if you think of this rotor, then it has to cover this much of distance, circumference 2 pi r, right? Let us say this is r. 2r is nothing but diameter, we know that. And this one, if you think of this one, then this has to rotate in this complete diameter. Means this one has to cover this much distance, total distance covered by this one. Radial distance covered by this one is more. So here if you think of, it is going to rotate by 2 pi r, let us see, capital R. Let me consider this radius as capital R here. Right, see here. Now, very easy, chill, see here. Radial velocity. Velocity means what? Speed. Speed means what? Distance upon time only. We know that the time taken by this one to rotate 100 rotations is how much? 1 minute. Time taken by this one to rotate 100 rotations is how much? 1 minute only. So, which means time taken for both of them is constant. That is what I was saying. So, if time taken for both of them is constant, then distance. So, if you see here, for this first one, if you see, distance is less, no? Distance is less and this particular circumference is less. The moment the circumference is less, radial velocity is less. So, for this one, if you see, here if you see for this one, radial velocity is less. Radial velocity RV is less. Whereas, if you think for this one, radial velocity is more. Now, what is the effects of it? What will be the problems of it? Let us see. See here, if I say that radial velocity has increased, then what is going to happen? Centrifugal forces and radial forces will also increase. If radial velocity is increased, centrifugal forces as well as radial forces will increase, which means mechanical stress will also increase. Now we know that design of insulation, if you think of design of insulation, if you think of it is also dependent on mechanical stress. Already we have discussed this. Design of insulation depends on mechanical stress, which means if mechanical stress is more, then for the same voltage rating, what is going to happen? Insulation will fail, right? So see here, again, see here, very easy. See, focus. If radial velocity is increased, mechanical stresses will increase. Why mechanical stress will increase? Because centrifugal and radial forces have been increased. See here, again, very simple. Radial velocity increased. Because of that, what happened? Centrifugal and radial forces also increased. The moment centrifugal and radial forces increased, mechanical stress also increased. Then, after when mechanical stress is increased, we know that for a same voltage rating, if the mechanical stress has been increased, for example, this is a insulator. It can, let us say that this insulator can block 100 volts. Block at 100 volts. Right? Now, the moment I apply some mechanical stress here on this particular insulator, what is going to happen? Will it block the same 100 volts? No, it is going to then block probably 70 volts. But now just imagine that your machine is operating at 100 volts only. Which means what is going to happen? Dielectric failure is going to happen. Which means, see here, what is going to happen? See, when your diameter is more, what happens? Radial velocity increases, because of which mechanical stresses increases, because of which insulation failure can happen easily. Whereas when your diameter is less, what is going to happen? When diameter is less, see here, what is going to happen? Radial velocity is less, which means mechanical stresses are less, which means insulation failure will not happen. That is the reason, one more point, conclusion. What is our conclusion? What is your conclusion, sir? See, conclusion number 5. Diameter of the cylindrical rotor is less. Diameter of the cylindrical rotor is less. That is what we have understood. Yes. So now, if you see here, there was one author named as N. Parker Smith. And notation. There was a person, name was notation. Notation solved one problem of this Parker Smith book, and he gave one derivation, right? And that particular derivation, if you see, moral of that derivation is important for us. Derivation is not at all important for us. This is a reference for you. If you are so much interested into electrical engineering, you can just go through it. Anyways, derivation is not important for us, but what he said, that was important. What he said, see here. Put 3 stars here. What he said, that power handling capacity of machine is determined by volume of air in the air gap. What did he say? He said that power handling capacity of the machine is determined by volume of air in the air gap. Now see here, which means, what does that mean? If volume of air is more, then in that case what is going to happen? Power handling capacity is also going to be more. If volume of air is less, then what is going to happen? Power handling capacity is going to be reduced. That is what he said. Now see here what I am saying. We have already seen that for our cylindrical rotor, we have already reduced the diameter. Am I right? We have already reduced the diameter of the rotor, cylindrical rotor. Why? Because of radial velocity. Radial velocity is less, because of which mechanical stress is less. So then insulation failure problems will not occur. That is what the reason was. But what has happened because of that? See here, this is rotor, right? Since the diameter of the rotor has been reduced, diameter means this one, this diameter. Since it has been reduced, volume in the air gap has also been reduced, right? Because see here, for example, let me think of red. Let me have a red rotor here as usual, and let me have blue stator. Right? Now let me take one more. Now see here, if you say yes, air gap here and air gap here is same. Yes, air gap here is same. But if you think of the total air contained here, and if you think of the total air contained here, you can clearly see that here the volume of air is more. Volume of air here is more. Whereas here if you see, volume of air is going to be less. By observation itself, right? See here, you just observe these two images. Air gap is same. I am not at all changing the air gap. Just what I have changed, diameter. When diameter of rotor has been reduced from here to here, this was the initial diameter, let us say. This was, let us say, diameter D1, and then it has become D2, such that D2 is less than D1. So initially, if diameter was big, then in that particular case, what has happened? For the same air gap, you have got volume of air is more. Whereas here, what has happened? When diameter has been reduced, what has happened? Volume of air here is decreased. So, but then we already know that this structure we cannot have. Why? Same reason. Radial velocity, mechanical stress, insulation problems. So we need to go with this structure only. So what can be done in order to make volume of the air same as this one? What else can be done? Only one thing. By increasing the radial length. Means, if I increase this active length here, if I increase of this rotor, then if you see, air will be here also around this active length, which means volume of air will increase or not? Definitely it will increase. So what is another observation from here? It is that diameter of a cylindrical rotor is less, but active length is going to be more. Let us write that. So this is going to be if you think of, see here, focus. Diameter of the cylindrical rotor is less, whereas active length of cylindrical rotor is more. Why it is more, we have understood. Why? Because power handling capacity is proportional to volume of air. Anyway, see here. Now, student may ask me, sir, cylindrical rotor can rotate at higher speeds, right? Now, you just tell me one thing, sir, that, yes, this one. Yes, this one. Sir, you were speaking about all this, right? Friction losses and all, noise and all, right? Just tell me one thing. Yes. Sir, please tell me, if rather than having a cylindrical rotor here, can I have salient pole rotor? If rather than cylindrical rotor, if I have salient rotor, what is going to happen? Let us see. If here rather than cylindrical rotor I had salient rotor, what will happen? We already know that salient rotor is rotating at, we rotate at low speeds only. Already we have discussed. So if my salient pole rotors are going to rotate at low speeds only, then this problem of radial velocity will not even occur. I hope you are understanding my point, right? See here, this problem was occurring. Why? Because they were actually rotating at high speed, rotating at high speed, rotating at high speed. But this rotor, salient rotor which is there, it is not rotating at high speeds, which means here in this case diameter can be more, right? Anyways, let us think of next. Now see here, let us think of frequency. F is equal to frequency. Frequency is going to be what? Pn by 120, right? Space to time, right? Space to time. So frequency is nothing but Pn by 120. Now see here, what is going to happen? In case of a cylindrical rotor, we know that number of poles is going to be less. Why? Because we want slot per pole to be more. That is the reason number of poles can be incorporated in the rotor will be less. Yes, less, no problem. Now, what about N? What about N, sir? Let us see. See here, I know that I want frequency of 50 Hz in India, right? I want frequency of this one, right? So if my poles are reduced, if I want to have 50 Hz frequency and my poles are reduced, which means speed has to be increased or not? In order to have same, for example, see here, F is equal to Pn by 120, right? So for something, for example, if you think of, let us say, poles are, for example, poles are 4. Let us say 4 poles, and this is 120 only, and let us say speed is let us say 1500 rpm. Let me think of that. This is poles, number of poles is 4, and this is nothing but speed 1500 rpm and 120 divided. What is going to happen? 0 gets cancelled. 4 ones are 4 threes are, you will get 50. Right or wrong? Right? So this is for, let us say, case 1. Now here thinking of, in order to have the same 50 Hz, frequency, see here, if my number of poles are reduced, which means speed has to be increased or not? Now if you think of, there is a beautiful coincidence. So if you think of here, very simple, in case of cylindrical rotor, if you see, we have got a beautiful coincidence. It is a beautiful coincidence. What is the coincidence? Sir? Coincidence is that in case of cylindrical rotor, if number of poles are reduced, we can operate it at higher speeds. That is the beauty, so that you get the same frequency, right? This is nothing but about the cylindrical rotor. Now see here. So now we have understood everything, but then student will ask me, sir, but whether we should use cylindrical rotor or salient rotor, which one is better? Let us see. Actually, you and me, we are all electrical engineers, and we have no right to select between cylindrical rotor and salient rotor, especially when we talk about generator. In case of motor, we can select. if for example I am operating the synchronous machine as a motor, then in that case I can select whether to use cylindrical rotor or a silent pole rotor. But when we are talking about generator, I cannot decide it. Who will decide? Mechanical engineer will decide. Means what, sir? Means very simple. Mechanical engineer, or we can say, in case of synchronous generator, we know that rotor has to be rotated. Now, who will rotate it? Prime mover. So prime mover will decide. Prime mover will decide. Meaning that, see here, prime mover will decide means what? See, very simple. Prime mover, if prime mover is rotating at high speeds, prime mover is rotating at high speeds, then I will use cylindrical rotor. And if the prime mover is rotating at low speeds, then I will use salient. I hope it is clear. Now, let us focus on prime mover for some time. See here. Let us think of prime mover. Let us see, I have this, what do you say, hub or something. Rotor only, for example. And let me have this. This is a turbine. This is a turbine. Python turbine. Now see here. Let me stand here and let me have some, this is me, and let me have some stones here. Right? Now what I will do is, one by one I will try to throw the stone here. I will throw the stone here on this. One by one. So the moment, for example, this first stone comes here, goes here. Then what is going to happen? This turbine blade will now come here. And the moment this blade comes here, what will happen? This will fall down. Stone will fall down. Right? So, the moment this stone hits it, what is going to happen? Heat is going to be produced or not? Heat is produced or not? Right? Now, you please tell me, what is stone? Stone is solid or? Stone is solid. Solid or liquid or gas? Solid only. Basically, in our practical things, we are not going to use stone. But this is just for understanding purpose that heat is going to be produced. Now, let us think of water. What I said, in case of stone, if you see, in case of stone, when we were talking about stone, what was there? Heat was produced or not? It was produced, yes. So, when I am throwing stones, I cannot rotate it at higher speeds, which means heat is produced. Heat is produced, which means what? Cannot rotate at higher speeds. Cannot rotate at high speeds. Whereas, if you see here, let me think of water now. For example, if I have water here, and if water is falling here, this will move here, water will come down here again, right around. In this case, the heat produced because of water. Heat produced because of water. Right? It is going to be less than the stone. Right? Which means, with respect to stone, here in this case, heat produces less because water will go smoothly. So, water will follow. See, this is the turbine blade. Water comes, water will go smoothly. When stone comes, heat will be produced. Anyways, see here. So here if you see, this is going to be less. So better than this or not? Means more speed than stone. It can rotate at more speed than stone. Right? Now, let me think of gas, or for example steam for that matter. If we think of gas or steam, what is going to happen? If I throw this steam here, then what will happen? Steam will smoothly move away. Steam will smoothly move away, which means heat produced by the steam, heat due to steam is going to be more or less, which means it can rotate at more speed than water. Right? Moral of the story, moral of the story. See here. Moral of the story. Moral of the story, see here. Out of these three, stone case, water case and steam case, if you think of stone case as it is, we don't use. Water and steam, if you see, what is going to happen? Heat produced due to water is more than heat produced due to steam. Right? So this one will rotate at low speeds as compared to steam, and this one will rotate at high speeds as compared to water, which means in case of steam turbines, steam or gas turbines, what is going to happen? Cylindrical rotor is used. Because cylindrical rotor can rotate at higher speeds. So let me write this in conclusion. So the seventh one. Seventh one is what? Yes. Cylindrical rotor used in steam or gas turbines. That's it. Please note all of this. All of these are for cylindrical rotor. Thank you.